As Monty Python would say, now it's time for something completely different. I'm working on my British accent. So the next speaker is Dominique Berry from Florida A&M University. He's been working this summer under the guidance of Bob Harmon right here at Ohio Wesleyan. And the title of his talk is Determination of Star Spot Latitudes on LO Pegasi Using Multiple Photometric Filters.
Hello, I am Dominique Berry. As Dr. H.K. said, I am working under Dr. Harmon here at Ohio Wesleyan University. Today I'll be talking about latitude resolution of star spots on LO Pegasi using multiple filters. Star spots are cooler, darker regions of the stellar surface known to be manifestations of a high magnetic field. A better understanding of star spots and the processes behind it, the way they work, translates directly to a better understanding of our own sun and its sunspot activity. Now, a more detailed model would be a great help in understanding that process. So, my project focuses on the observation of LO Pegasi. LO Pegasi is a variable star with a period of approximately 10.15 hours. It is suitable for observation from the months of May to November, which makes it perfect for summer research. We take images similar to the one here on nights where it's clear enough that we feel like the data will be reliable, and we take these images through 4 photometric filters. We use an infrared filter, a red filter, a visual filter, and a blue filter. Taking these images allows us to perform a process called differential photometry. Differential photometry involves comparing your target star to a comparison star, which you know to be of constant brightness, and using a check star to make sure that process isn't going anywhere. In our image here, we have our target LO Pegasi marked by the leftmost red concentric circle. Our comparison star is SAO 89758, and our check star here. After performing differential photometry, we can plot the apparent magnitude of LO Pegasi as a function of rotational phase, with rotational phase being like if the star spot is pointing directly towards you, it's at 0 rotational phase, and it's at 90, 0.25, 0.5, 0.75, and it goes back to 1 and it repeats like so. Now, using these images, we can use a technique developed by Dr. Harmon and invert the light curves to get a model of the stellar surface. The program divides a sphere into partitions similar to the image here, and then it varies the brightness of each of those partitions to attempt to match the light curve as best it can. Now, unfortunately, a single light curve does not have a single solution. For example, we had a completely flat light curve, then one possible solution could be to have a sphere with uniformly bright partitions, but another solution could be to have a sphere where there are a series of dark and light partitions whose contributions cancel each other out as the star rotates. Now, as with any ambiguity problem, we provide more information to the program to try to get it to limit the number of solutions to a much smaller set as opposed to a completely ambiguous set. And we do that by providing multiple filters to invert at the same time. Now, have you ever looked at a picture of the sun and wondered why the center is brighter than the edge of the sun? If you have not, that was a great time to do so. A star is not completely transparent, and as a result, you can only see a certain physical distance within the star. This is exaggerated greatly here. And this distance is independent of whether you're looking at the center of the star or at the edge of the star. And when you're looking at the center of the star, you're looking directly towards the star's core, so you see a higher temperature than you would at the edge where you're looking off center. Now, Planck's law of blackbody radiation states that a higher temperature blackbody will emit more electromagnetic radiation than a lower temperature blackbody. A star being a near blackbody object largely follows this same law. As a result, because you see a higher temperature in the middle, it appears brighter than along the edge. Now, limb darkening is dependent on the distance into the star that you can see. Notice in the animation here, as the distance, the green line decreases, the levels to which you can see get closer together. And this subsequently causes the temperature difference to get smaller. And it causes and you can see their point curves get closer together as the distance decreases. As a result, limb darkening is not as severe when you can only see a small distance into the star, and is more severe when you can see a large distance into the star. Limb darkening affects stars at different latitudes differently. In this figure here, we have two stars. Each of these stars have identical star spots patterns, one at a high latitude and one through the equator. This first star exhibits no limb darkening at all. And you can see in this graph here how the first star spot affects the light curve. And it's a small. And then you have the second star spot, and it affects the light curve differently. Now, these star spots are the same size, but because the star is a sphere, the star at the higher latitude is tilted relative to that angle of observation. So it projects to the lower area and affects the light curve less. Now, if we move over to the case where there's a lot of limb darkening, then the first star spot, as it moves at a higher latitude, is moving across a dimmer background. As a result, it affects the light curve less. And this second star spot, as it moves through the center, is moving through a greater portion of the bright part of the star. And it affects the light curve even more. Now, the point of me showing you this is to show that limb darkening can change the way a star spot affects a light curve in both a positive, as in it exaggerates the effect, and a negative, is like it lessens the effect. Now, here we have contrast ratios. Now, consider we have a star at 6,000 Kelvin and a star spot at 3,000 Kelvin. Now, if we look along the blue band, we can see that the difference in the two curves is much greater in the blue band than it is at the red band. And this holds true across the blue, green, red, and infrared spectrum, which would be our four filters. The green, our visual filter, contains a range within the green, roughly. So, knowing this relationship here, we can calculate the amplitudes of the different filters' light curves relative to one another. And how this will show up on our actual light curve will be affected by the latitude of the star spot and the limb darkening, as discussed in this previous picture here. And if you measure the distance between the difference between the expected effect of your star spot and its actual effect on a filter's light curve, and knowing the extent to which your target is affected by limb darkening, you can calculate the latitude of the star spot. And this makes it easier for our program to limit the number of solutions and give us a much smaller set to look at to see which one we feel is more reliable. Now, I have a few acknowledgments. I would like to thank the National Science Foundation for funding my research, Iowa Wesleyan University for hosting this program and allowing me to be a part of it, and Dr. Harmon for providing a lot of insight and help over the summer.
Any questions for Dominique? Sean?
So when you show the limb darkening picture of the star spots, is it I don't know how to ask this. Is this the case where a small star spot at a high latitude would have a similar effect than a bigger star spot at a low latitude? Like, how can you tell? You mean, because a bigger star spot would make it dimmer too, right?
Yes.
So how can you tell which one it is? Is it big or is it high? You know what I'm asking?
Are you asking if we can tell the difference between a large spot up here and a small spot in the middle?
Or possibly vice versa, to get two. What I'm really asking is it possible for two different size and latitude star spots at different places on the star to give the same light curve.
Yes, it is possible, which is why we use multiple filters and account for limb darkening,
Right.
because that will,
So even, so once you do that, you can more or less uniquely define where and what size the star spot is?
yes, more or less.
Yeah, it helps a lot. So basically, you could have them look identical through one filter, but
The
not
combination
but
is-
not the same through a different filter because of the different amount of limb darkening. And so that provides an additional constraint on limb spotting.
That's really cool.
You mentioned the observations that were made. Were they made here at Ohio Wesleyan?
They were made at Perkins Observatory, which I believe is around 3 miles away from here. Is that right? 3 miles?
Yeah, it's about 3 miles, and it's an embassy, so to speak. It's part of campus, but it's
Uh-huh.
disconnected from.
So were you involved in some of the observations too, or were you doing more analysis?
Yeah, I was there on those nights. We have a poster. Well, other group members that worked under Dr. Harmon have a poster outside, and they'd be happy to go more in detail with like the actual observation procedures with you. Or I'll be there so you can actually see.
Other question?
You mentioned that there are ambiguities. You're right. Your computational models. You
Yes.
set up some systems. Different systems have the same observational conflicts. Do you have certain assumptions that you make, like some plots come in pairs, or so, is it do those things go into the computational model or the theoretical model that you're putting in, or is it more of a Monte Carlo kind of thing?
We do have some assumptions, like star spots do normally come in pairs. On this particular year, we believe that LO Pegasi has a large polar spot. So its pair, I believe, would be on the southern pole, which we wouldn't actually be able to see. Or, well, I can't tell you whether it's the north or the south pole. It's the visible pole. But the non-visible pole, I believe, would have the other pair, and we wouldn't see the effect of that star spot.
You mentioned the pole as like, the star spot as like this year's star spot. How long is the lifetime of the star spot? How often are they changing?
On LO Pegasi, I believe the star spot cycle is about 1 year. So every year we see a different light curve.
Okay, I think I have one more question.
Is there analysis like this being done on like our own sun or other stars? Maybe Dr. Harmon knows.
Yeah, for our own sun, well, we can just photograph it. For other stars, even to the Hubble Space Telescope, they look like pinpoints. Optical interferometry is becoming possible now, where we might be able to start imaging them, which is exciting and terrifying at the same time, because it means we can see if these models are actually correct now. But the simulations suggest that we can get some reasonably correct results. But yes, there are other stars that are being studied with similar and different techniques. It's a very active field.
Okay, let's thank Dominique again.